Welcome back. I hope you had a wonderful weekend. Let's get started with our next chapter. Welcome back. Today we will cover Chapter 11, the t-test for two related samples. After this chapter, you will be able to understand the structure of research study appropriate for repeated measure t-hypothesis test, and repeated measure is just another word for correlated sample t-test. You will be able to test the mean difference between two treatment conditions using the repeated measure t-statistic. You will be able to evaluate the effect size if needed, again using Cohen's d or R-square, and also be able to establish a confidence interval. And then lastly, explain the pros and the cons of repeated measure and independent measure studies. The t-test for two related samples compares the means between two related sample means, or within subjects. So sample group 1 does something and you collect data, then the conditions are altered in some way and you collect data from the same people again. To analyze the results and to be sure that the observed differences are not due to pure chance, we conduct a t-test for correlated samples. The main difference between a t-test for independent samples and a t-test for correlated samples is that here the correlation can be used to reduce the size of the standard error of the differences between the sample means. Reducing the standard error of the differences can be a real advantage because the smaller the standard error of the difference is, the larger our t is going to be. Because in a correlated sample t-test, each participant is used twice, so the same participant is in each sample, we can compute the amount of error that is due to the variability of each participant, because there is no, since they're the same people, and use this to reduce the standard of error of the differences, thereby again increasing the size of t. Sometimes we try to approximate the advantages of a repeated measure design and use with what's called a matched subject design. So in this case, two separate samples are used, but each individual in the sample is matched. So 1-to-1 with an individual in another sample on a very specific relevant variable. Clearly in this case, the participants are not identical to their match, but this ensures that the samples are equivalent with respect to some specific variable. So we use a related or correlated sample design, meaning the same statistical calculations when we have repeated measures or when we have a matched sample. The t-statistic for repeated measures research design is structurally very similar to the other t-statistics that were done. Essentially, it is the same as a single sample t-test, and you're going to see that in a second when you see the formula. Only here now, it is based on differences in scores, which we're going to note with d rather than the raw scores of x. So we will look for the difference in score. So we have two samples. So the difference between, for example, before and after. So before would be the value we have for x1, and then after we do the measurement again, after something has been done to the sample, we measure it again, and then we'll see the difference. That's the difference in scores. So the formula is the mean difference is the sum of d, so the sum of these differences over n. So here, instead of looking at the differences between sample 1 and sample 2, we now look at the differences in scores between the sample before something was done to them and then after. That difference in scores will tell us the mean difference for the two samples. Let's look at the concept of the mean difference a little bit more in detail. Let's do the following example. You all probably heard that medication causes drowsiness, right? That's usually the warning that you see on the labels. So let's say we take a sample of 4 people and we let them play a video game. It's a car racing game where you're trying to have as little accidents as possible. They all have the flu. So we want to see if this flu medicine that we just invented, if that actually causes drowsiness. So we let these 4 people play a video game for 1 hour and we count the number of accidents that they have. Now we give them the flu medicine. An hour after they took the medication, we let them play the car racing game again and we count the number of accidents. So basically, we're counting the number of accidents they did before they took the medication and then after they took the medication. So our null hypothesis is that the medication does not affect the number of accidents. That means the medication would not cause drowsiness because there is no difference between the number of accidents they had before and after. Our research hypothesis is that the medication does affect the number of accidents. So we're not specifying if the accidents are going to go up or down. We're just saying the medication does affect. That means this is going to be a two-tail test. We said our sample, we had 4 people. So here we have Victor, Stephanie, Selena, and Amor. And we have them play the video game. We counted the number of accidents before they took the medication. So 215, 221, 196, and 203. The number of accidents for each of these people before. Then, again, we gave them the medication. We waited an hour, let them play the game again. And these were the number of accidents after they took the medication. So you can see for some of them, number of accidents increased. For some of them, the number of accidents decreased. What we want to know is the mean difference is the difference between before and after. So we just get the difference. We minus the after score from the before score. So here, 210 minus 215 is the minus 5. So that's the person that actually had less accident after they took the medication. For everybody else, we can see there was an increase. Now we add that up. That is the sum of the differences. So in this case, this would be 64. Because for the mean formula, for the mean difference formula, we need the sum of D, so the sum of the difference over the number of people. So that's 64 divided by 4. So the mean difference is 16. Here you can see all the formulas that we're going to be using for the related sample t-test. So we already said our null hypothesis would be that there is no difference. Our research hypothesis, there is a difference. And then our t-statistic for the correlated samples is based on this mean difference that we just figured out and also on the estimated standard error, just like before. But its notation is now SMD because it's the estimated standard error of the mean difference. The calculations are the same as before, the square root of the variance over n, and the variance of D is the sum of square over the degree of freedom. The sum of square looks just like our regular sum of square formula, just instead of x now, you can see that we are working with D, so with the differences. Let's continue with our previous example of the video games and the medication to calculate the related sample t-test. So we know we are after t, so we use the t formula. We need this t formula since we are doing a related sample t-test before and after. Here we know we need the mean difference. We just figured that out, that's 16. Again, the population mean difference is based on the null hypothesis that there is no difference. So that's going to be 0 again, but we also need the estimated standard error of the mean difference. So we have to write this formula down. Here we see that we will need to take the square root of the variance over n, but we don't have the variance. We know the formula for the variance is the sum of square over the degree of freedom. And the sum of square formula now is going to look very familiar to you, but you see again that it's only instead of x, it's based on the d's, on the differences. So when we have our data set from before, we know what we did is we took the differences between after and before, and we came up with a sum of the differences of 64. So we already have this value right here. We know n, but we also know we need the sum of d squared. And just like before, all we have to do is square our d values, add them up, and we get the sum of d squared. So now we just plug it in again. We come up with the sum of square of 596. Now we can plug that in for the variance and solve by 596 over the degree of freedom. We have 4 people, so the degree of freedom is 3. Our variance is then 198.67, and again, now we just plug it in here to solve for our estimated standard error of the mean difference. We get a result of 7.05. Please ignore this little line. So the end result is 7.05. And now we can solve for t. We know from previous that we calculated the mean difference to be 16. This again is going to be 0 over the 7.05, and we get a t-value of 2.27. And now we are doing exactly what we did before. We would compare this to the one that we would have found in the table as our critical value. We would see, is this larger than our critical value? Then we can reject the null hypothesis. If we would find that this would be actually smaller than our critical value, then we would have to say that the medication is not significantly affecting the number of accidents. But we'll continue with this later. For the repeated measure design hypothesis test, the numerator of the t-statistic measures the actual differences between the data, so the mean difference, and the hypothesized population mean. The denominator measures the standard difference that is expected if the null hypothesis is true, so that's the estimated standard error of the mean difference. We have exactly the same 5-step process as we did for the other tests. So step 1 being considering which test do I have to use and then state our hypotheses and so on. And here you can see an example of, for example, critical region for t with a degree of freedom of 8 and an alpha of 0.05. These would be the critical t values. Again, if we find our calculated t to be in the critical region, so in the blue, we would reject the null hypothesis. However, if it would be in the bulk, in the middle, we would fail to reject the null hypothesis. Once we find that our t is in the critical region and we can reject the null hypothesis, so there was an effect, we might want to measure effect size again. So effect size for the related samples is also based on an estimated coincidence d or of r squared, depending which one you want to use. An estimated coincidence d, again, you can see it's very similar, but now it's just based on the sample mean difference over the standard deviation. And r squared is exactly the same formula as it was before. And again, that gives us the percentage of variance that is accounted for by the treatment. Confidence interval to estimate the population mean difference is again calculated by taking the mean difference from the samples and adding and subtracting the product of our t-value times the estimated standard error. And the interval you get gives you a confident estimate that the value of the population parameter should be located in this interval. So what you should be reporting and what you will see in the literature is the means and the standard deviation, either in a statement or in a table. Then the concise version of the test results need to be reported. So you report the t-value with a degree of freedom, the significance level, and also the effect size. So for example, it would be t, degree of freedom in parentheses of 9, equals 2.43. The probability was smaller than 0.05, and the variance was 0.697. So the p tells us that the finding is significant to the 0.05 level. The probability that the finding happened due to chance is smaller than 0.05. R squared we have 0.697, meaning that 69.7% of the variance in the scores is explained by the independent variable, so by the treatment. Just like before, we can also do directional hypotheses and use one-tailed tests. Often the researcher has a specific prediction for related sample design. Let's use our example again. If we think that medication causes drowsiness and people play a video game and then they play it after they use the medication, most likely we think that they're going to have more accidents afterward if the medication in fact does cause drowsiness, right? We could have done a directional hypothesis saying that if you take the medication, so this is a treatment, then your accidents will increase. So in this case, we just stated our null hypothesis and research hypothesis directionally. So either we expect it to be larger or smaller. And then in this case, the critical region would be located in one tail. Each of the tests have their pros and their cons. The advantages of repeated measures design are that you require fewer subjects, because you use the same people before and after. This test is great because you're able to study changes over time. It also reduces or eliminates the influence of individual differences because you're using the same people. And there's substantially less variability in the scores. The disadvantages of repeated measure design is that factors besides the treatment may cause the subject's score to change during the time between measurements. So maybe something happened, and it's not really that the changes are due to the treatment, but something from the outside happened. Also, the participation in the first treatment may influence the score in the second treatment. So the idea of if you played the video game before, maybe you kind of remember that, oh, now there's a tree coming up, there's a car coming up. So actually having played the game before might be a reason why the accidents changed and not because of the medication. That's what the order effect is. Congratulations, another chapter done. See you next time.